Okay, in today's lecture, we are going to study the details for having done the quantitative analysis for PN junction diode. So herein, PN junction electrostatics are introduced again, but with a non-zero applied voltage across PN junction diode. So previously, when the PN junction diode is at thermal equilibrium, its own built-in potential, denoted as V sub VI, VBI, would be described with two sums of the sum of two terms. So one of the terms is KT over Q times ln the doping concentration on the P side divided by N sub I intrinsic concentration. And the other term for the summation is KT over Q times ln the doping concentration in the N side, not instead of P side, divided by N sub I. So we can have the comprehensive equation for a built-in potential VBI, as shown in here. So once you know the doping concentration on each side of PN diode, then you can simply estimate quantitatively the built-in potential voltage of the PN junction diode. So for example, if P side is doped like, okay, Na is 10 to the 17 per cubic centimeter, and N side is, suppose that the donor's concentration is 10 to the 16 per cubic centimeter. Well, definitely in the P side, there is a certain amount of donors, but that amount of donors would be much, much smaller than the acceptor's concentration. That's the reason why this area is denoted as P side. And similarly, the total amount of acceptor in the N side is negligible or much, much smaller than the donor's concentration. So in p-n junction diode analysis, whenever I'm talking about the N sub A in the P side, indicates Na minus Nd, which indicates the net doping concentration in the P side. What about the Nd in the N side? Whenever I'm writing down the Nd for the N side of the p-n junction diode, which means Nd indicates the net doping concentration in the N side, which is corresponding to the Nd minus Na in the N side. Okay, so simply plug in those two values into this equation, then you will get the built-in potential. But just for refreshing your memory again, once you know the 60 millivolts low that I have named, say 10 to the 17 for P side, then take a 7 here, and you can multiply 60 millivolt, then you're gonna get 420 milli electron volt, right? 60 milli electron volt. So in other words, 0.42 electron volt. So this indicates the energy difference between Fermi energy level and the intrinsic Fermi energy level in the P side. Definitely EF is lower than EI because it's a P side. And what about the N side? Use the 10 to the 16. So take a 6 and times 0.06 electron volt, then you're going to end up with 0.36 electron volt, which means the energy difference between Fermi energy level and intrinsic Fermi level in the N side. So by simply summing up those two values, so this 0.42 indicates corresponding to this term for P side, and 0.36 electron volt is corresponding to that side. So by simply summing up those two values, then you're going to end up with a 0.78 electron volt in this specific example. So maybe when you're an undergraduate student, you had a chance, or when you had a chance to take a microelectronic circuit analysis class, then you may remember the for a given nonlinear circuit, including diode or diodes, the diode can be modeled with a constant voltage drop model, which means a certain amount of voltage has always dropped across the PN junction diode. That amount, that constant voltage drop across the PN diode comes from, physically be originated from this built-in potential, okay? So whenever you had a chance to look at the constant voltage drop model for PN junction diode, please remember the built-in potential is identical and equal to the constant voltage drop used in that model. Okay, so depending on the doping concentration on either side of PN junction diode, you're gonna designate and design your own built-in potential value. Okay. All right, let's move on to the next subtopic, that is depletion width, denoted as W. So when we are doing the analysis for PN junction electrostatics under thermal equilibrium, the depletion width is divided into two sections: depletion width in the P side and another depletion width in the N side. So by summing up those two depletion layers width, we can get the total width of depletion width layer in the PN junction diode. So the detailed equation has been already described and derived. But previously, if you go back and to take a look at the equation for depletion width of PN junction diode at thermal equilibrium, you're gonna find out that this term was VBI, but now it is VBI minus VA. So instead of using VBI, you simply substitute, uh, you simply replace VBI with VBI minus VA. That's it. Okay. So instead of VBI, please plug in VBI minus VA. So this value would be varied depending on the biasing condition for your PN diode. Okay. And from this equation, you're going to derive the depletion width in the P side, denoted as X of P, and the depletion layer width in the N side is denoted as X of N. So depending on the doping concentration, right, on the other part of the PN diode, suppose that this is a depletion layer width on the P side, but it is very dependent of the doping concentration on the N side, okay? And what about here? The depletion layer width on the N side is very dependent of the doping concentration on the P side. But in summary, as you have already learned, the total width of depletion layer is very dominated by P side or N side? No, lightly doped side. Okay, so once either side of PN junction diode is relatively lightly doped, then that reason, P side or N side, depending on the doping concentration on each, would determine and dominate the depletion layer width. Okay, so the lower the doping concentration is, the more you can find out the depletion layer in the PN diode. Okay. All right. Then now let's move on to the electric field distribution, denoted as E sub x, E of x. So let me write down how the electric field is distributed out across the PN diode. So definitely the origin point indicates a physical or metallurgical junction between P side and N side. And as we have learned, a certain amount of depletion layer has been formed already, and electric field has been formed, and its a peak value maximum electric field intensity can be found and observed at the metallurgical junction or physical junction. And herein, because we are doing the quantitative analysis for PN diode, let's think about the physical meaning of the slope. I mean the dE dx. Okay, how sense the electric field intensity can be varied as a function of x. Okay, in the N side. So which term, what kind of things would determine the uh, sensitivity of electric field with respect to displacement or position in the P side, in the N side? So as we have known already, this uh, slope is very dependent of doping concentration. proportional to the doping concentration. I guess I need to double check the equation again. Let me see. Where is the equation? I guess I need some time. Yeah, later on, I'm going back to this part again. I guess I lost my note. Anyhow, herein the thing that I would like to deliver to you is the meaning of area. Area means integration of electric field. So what is the physical meaning? Yeah, once you take an integration of electric field with respect to x, the quantity, physical quantity is corresponding to the potential. Okay, but what kind of potential can we get from the area? Think about the energy band diagram across the depletion layer, and think about the charge density block diagram again. Okay, then you're gonna end up with, you may remember this one. Just as simply, you have done the integration work by solving this equation. From 0, here minus xp plus xn. So suppose that here the reference potential 0 volt has been defined, and now, you know, here this should be the first order polynomial equation. So just plug in first order equation, then the meaning of area, or the equation for describing area is second order polynomial equation, so that you're gonna see this some curvature, okay, parabolic shape, and in this area another straight line, simply speaking, y is equal to ax plus b. So this form of equation can be expected to describe the electric field as a function of x, and just plug in this integration, and the equation for this area would be the second order polynomial equation. So another parabolic shape would be obtained for the depletion layer on the n side, and then you're going to end up with a constant voltage value. So this voltage value would be definitely matched to the built-in potential. Okay, so just you remember this equation. Potential is defined as the integration of electric field. In other words, dE dx, no, dV dx is equal to minus C. So if you remember this, those are two equations you're gonna get, and you're gonna estimate, and you're gonna draw the potential distribution along the x direction as shown in here. Okay, so this area indicates built-in potential. However, since we are applying a certain amount of applied voltage, so this potential barrier height would be, instead of VBI, we should take care of a VBI minus VA, so that the area is corresponding to the, instead of VBI, it should be VBI minus VA. Okay, so once you know the electric field distribution by estimating the area of this plot, then you're gonna get VBI minus VA. Okay, all right, and now let's move on to the next slide. Previously I have drawn the electric field distribution along the x direction, so like that. So this area can be obtained by taking the integration of electric field with respect to x. So we have done this, and that value is corresponding to the VBI, built-in potential, minus VA. But the thing that the easiest way to estimate the area is, you can calculate the area of a triangular, right? So this and that height. So the side length of the triangular is, just simply speaking, the depletion width, right? So this point, edge point, is minus xp, and the other edge point is plus xn. So this plus xn plus xp. Xn plus xp is corresponding to depletion width, so that the bottom side length is corresponding to W, depletion layer width. What about the height of this triangle? Yes, this is 0, and that is electric field max. So maximum electric field intensity, or electric field at x of 0. So instead of it, I simply write down electric field of 0. Okay, so this multiplied by depletion layer width divided by 2, we're gonna get the area of the triangular shape. Okay, so from this equation, once we know the doping concentration on p side and n side, we can estimate the VBI, and VA means how much voltage you have applied, so you know this value. And depletion width is very dependent of doping concentration. Going back to the last slide, where is it? There we go. Here, the depletion layer width can be obtained once you know the 2 epsilon s dielectric constant of semiconductor unit charge, 1.6 times 10 to the minus 19 coulomb. VBI minus VA, you know the VBI, you know the VA, and you know the doping concentration on each side. Then you're gonna get the value for depletion width. Then plug in that value into this equation. And then you can get this value. In other words, the peak electric field intensity can be obtained once you know the W, VBI, and how much voltage has been applied across the PN diode. Okay, so you may estimate, you're going to be asked to calculate and estimate the value of peak electric field in for a given PN diode. You can do that. All right. And next topic is for a one-sided PN junction diode. One-sided means, you know, PN diode is given, and once either side of PN diode has been very heavily doped, so such as P++ N, or what else, PN++, like that. So either part of the PN junction diode has been very, very heavily doped or degeneratedly doped. We can call it as one-sided PN junction diode. And previously, as I have mentioned previously, the depletion layer width, total depletion layer width is very dependent of lightly doped side. So in this one-sided PN diode, for this specific PN diode, one-sided PN diode, the N side is lightly doped, so that the depletion width is very dependent of the donor's concentration in the N side. Okay, so here N should be substituted with N lightly doped side 1. Okay, then in this specific case, P plus N junction, take a donor's concentration and plug in here, then you're gonna obtain the depletion layer width. Okay, so once you for a given one-sided PN diode, the depletion layer width can be obtained using this equation. But since if you're very screwed up with and very confused with two different equations for one-sided junction diode and the other equation for just regular PN junction diode, then just always use this depletion layer width equation for regular, and that is still valid for the one-sided PN diode. Okay. So by estimating the depletion layer width, then you're gonna get the peak electric field. Okay. And then you're gonna end up with this equation. Okay. All right. So now I have done the quantitative analysis for PN junction diode at non-thermal equilibrium state. Okay. So the key message is you can adopt all the equations you can use. You can take advantage of using all the equations that you have obtained at thermal equilibrium, but with VBI minus VA instead of VBI. Okay, that's a key message. Now, before deriving the quantitative equation for current voltage characteristic of PN junction diode, let me briefly tell you how the electrons and holes are moving toward the other side across the PN diode. So as you know, the PN junction diode consists of two parts, P side and N side. And left hand side is, P side, and right hand side is N side. Well, okay. And let me draw the energy band diagram for PN diode at thermal equilibrium. Since a single system has a single value the Fermi energy level when it is under thermal equilibrium state. So EF, take a look at this solid colored line. EF has been set, and left hand side is P side, right hand side is N side. So since P side, Fermi energy level should be below the intrinsic Fermi energy level, and this energy difference is very dependent of the doping concentration. So once you know the 60 millivolts law that I have taught you, then you're gonna simply estimate how much the energy difference should be there. What about here? This is N side. So depending on the doping concentration in the N side, you can estimate the energy difference between EF and EI on the N side. Just simply use a 60 millivolts law. So here and there, so you can see that the depletion layer has been well formed. And the majority carriers in the N side is electrons, right? So most of the electron has existed near the conduction band edge, as we have learned by following the Fermi-Dirac distribution. So most of the conduction electrons are well existing near the conduction band edge or E sub C. So because of the energy barrier height across the PN diode, most of the electrons can never overcome this energy barrier height. However, very tiny amount of electrons which has a very high energy would freely move into the p side. Okay, so similarly, in the p side, the majority carriers in the p side is definitely holes, and those holes are distributed out following the Fermi-Dirac distribution, so that most of the holes are existing near the valence band edges. However, because of the potential energy barrier height across PN diode, most of the holes can never overcome this energy barrier height. Again, just for your information, the minus y direction indicates the energy of holes increasing direction, okay? And the plus y axis indicates the energy of electrons increasing, okay? So this hole is kind of hot hole. Hot hole means holes with very high energy. So very tiny number of very small or almost negligible number of holes would have a chance to move into the N side. Okay. But previously I mentioned that very small number of electrons and holes would move onto the other side. That means the current would be formed by hole, and another current value would be formed by electron. So this current should be cancelled out by opposite movement of electrons and holes. Otherwise, this PN junction diode under thermal equilibrium state would form a certain amount of current. This is contradiction because we didn't deliver any energy, any voltage across the PN diode. How come the PN diode can flow a current? It is impossible. So we should imagine what kind of electron and holes movement to cancel out this and that movement. The answer can be found how the minority carriers instead of majority carriers, how minority carriers are moving into the other side. So this is p side. So the minority carrier is definitely electrons. So very small amount of electrons, but existing near the edge of depletion layer width, it should move on the left hand side or right hand side once if I limit the space into one-dimensional area, one-dimensional space, then electron would move left or right. Did you remember the diffusion lengths, the physical meaning of diffusion lengths? Yeah, diffusion length indicates the average distance that a minority carrier can go and move without any recombination with majority carriers. Okay, so within the one diffusion length, the minority carrier's electron in p side would survive without recombination. So it is possible for these electrons get into the depletion layer width, and because of the built-in electric field within the depletion layer width, this electron minority carrier in the p side would move by drift mechanism into the n side. Okay. Similarly, you can imagine how the minority carrier in the n side, which is hole herein, within a one diffusion length away from the edge of the depletion layer width, say that is 0 and that is plus xn, so xn to xn plus lp, the minority carriers holes in n side, right? If hole is existing within this area, it would be possible to move into the depletion layer width. Then the electric field is formed from n to p, so this hole would be drifted toward the n side. So this minority carrier electron and holes movement should cancel out the majority carriers movement. So that is the main reason why there is no current at thermal equilibrium. Okay, so we have understood the current is not flowing at thermal equilibrium. However, microscopically, the electrons and holes are still dynamically moving toward the other part. So previously, maybe if you taken my class last semester, you may remember that all the electrons and holes in a silicon material would be in the dynamic situation. So dynamic situation means very quite opposite concept of static situation. Static situation means suppose that there are two electrons in the n side. That two electrons would be still available 1 day later and 10 days later. But if that n side material is in dynamic situation, maybe tomorrow you're gonna get two electrons, but that two electrons would be very different from the two electrons that you have seen today. Okay, so over time, the total amount of electrons are still well remained and kept. However, the electrons that you have observed at a time t of 0 would never be again observed at the time of non-zero. Okay, so that describes well the dynamic situation. Okay, all right, now let's move on to the next one. What if the positive voltage, or suppose that the n side is grounded, 0 volt, and higher voltage VA is higher than the voltage applied onto the n side, which is 0 volt. So that is the reason why I'm saying positive voltage is applied across PN diode. Then what would be happened? Qualitatively, not quantitatively. We're gonna tackle quantitative analysis sooner or later, but herein, take a look at what kind of things would be occurred. Yes, here, the built-in potential, QVBI, minus VA. So depending on how much forward bias has been applied, the energy barrier height from the perspective of electrons in the n side would becomes lower and lower. So that originally only hot electrons would move into the p side, but now because of the lowered potential energy barrier height, so many electrons are ready to move into the p side. But here I said many, but not really many. Think about how many electrons are available depending on the energy level. So I said energy difference is linearly increasing, but for a given energy state, the number of electrons are exponentially increasing. So simply speaking, if say this is 0, 1, 2, 3, 4. So energy is increasing at a linear pace, but at each energy level, the total number of electrons is exponentially increasing or decreasing. So if you increase the voltage, forward voltage across PN diode, the number of electrons that can participate in moving into the P side would increase exponentially. So that is main reason if you go to this current versus voltage plot for PN junction diode, once you increase the bias, forward bias at a linear pace, say 1, 2, 3 volt, then the amount of current is not increasing 1 to 3, but increasing 1 and another 3, so total 4, 1, 3, and next one is 3 squared, so 9. So 9 plus 4 is 13. So you're going to see that the current level is here, 13, this point and that point, and one comma con here. So by connecting those data point, you're going to see that the current voltage curve would follow the y is equal to exponential x. So why exponentially increasing? The physics or physical origin can be found from the Fermi-Dirac distribution, or as we have learned, how many electrons can be found at each energy state in conduction band. So in the conduction band, every single energy state, you're going to see that the number of electrons are exponentially decreasing. Why is that? Well, the basic is, that once you know the density of state times Fermi function, remember the Fermi function. The meaning of Fermi function is for a given energy state, how likely a single electron can be found. Okay, so that Fermi function is following the exponential function. Do you remember the 1 over 1 plus exponential e minus ef over kt? So because of this term, the electrons distribution in the conduction band is following the Fermi-Dirac distribution, so that as energy is linearly increasing, the number of electrons available at each energy level would be increasing exponentially. That is the main physical origin why in the diode, if you increase bias linearly, your current value across PN diode is exponentially increasing. Okay, so you should understand the physical origin why diode is well flowing. Tremendously amount of current can be flown once forward bias is applied in the diode. Okay, so similarly, you may imagine how holes are moving into the N side from P side. So again, the hole is following the Fermi-Dirac distribution, so that once this potential energy barrier height has been lowered by, lowered linearly, then the total amount of holes that can participate in flowing into the N side would increase exponentially. So that is another reason why in the diode the current is exponentially increasing as the bias is linearly increasing. Okay, then we have done the quantitative analysis for the forward bias once VA is higher than 0. Then the last one is current flow under reverse bias. So let's take a look at how the electrons and holes are moving once potential barrier height has been increased a lot because of the reverse bias. Original energy barrier height is Q times VBI. However, herein, the barrier height has been increased by VA. So herein, note that even though we are applying a negative bias across PN diode, let's take a magnitude of it, then, and plug in here, then you can use a plus symbol, then you're gonna get the increased energy barrier height under reverse bias. Interestingly, all the electrons available in the conduction band would never get into the P side because of very high energy barrier height. Similarly, all the holes in the valence band would never overcome this energy barrier height. So straightforwardly or intuitively, you may guess that there is no current across PN diode because of the increased energy barrier height. That's true, but we have missed one more point. The missing point comes from this electron and holes. In other words, the electrons and holes, minority carriers in the p side and another minority carriers in the n side, would affect and would contribute to a very tiny amount of current flow under reverse bias. So let's take a look at how those carriers can move into the other side in the PN diode. So this electron, which is a minority carrier in the p side, would get into the depletion layer width once it is existing within a diffusion length away from the edge of the depletion layer. And similarly, another hole which is existing within one single diffusion length away from the edge of the depletion layer, then this would have a certain amount of possibility to get into the depletion layer width. Once it is injected into the depletion layer width, then there is electric field. So electron, this guy, and hole, that guy, would drift, moved like this, because it is drifting, gaining kinetic energy and losing its own kinetic energy because of a scattering event. There are three major scattering events, right? Phonon scattering and impurity scattering and carrier to carrier scattering. So if you're not very familiar with those words, please review what kind of scattering events would be happened and occurred in a single crystalline silicon material. Okay. Otherwise, you should drop by my office hour and please ask and consult with your colleagues and friends. Then you're gonna feel more convenient. Anyhow, so by going through those three major scattering events, this hole and that electron would get to the n side and hole would get to the p side. Then this flow would cause and make and form a very tiny amount of current flow. But one more interesting point is this electron would never be associated with the energy barrier height here. Whatever the height of energy barrier is, the total amount of injection of electrons from p to n side is very independent. Whatever the energy barrier height is, the total amount of injection would be constant. So there is a simple analogy. There is a waterfall. You know the waterfall, right? So depending on the height of waterfall, can you imagine that this waterfall would flow more water? Is it reasonable? The higher the waterfall's height is, the more the water can flow throughout the waterfall. Is it true? Does it make sense? No. How much water is flowing is nothing to do with the waterfall's height. So similarly, for this given energy band diagram, how much reverse bias has been applied is nothing to do with how many electrons would be injected into the depletion layer. The key now or key factors in determining how many electrons would get into the depletion layer width is the function of diffusion length. The longer the diffusion length is, the more the number of electrons can get into the depletion layer width. Okay, the number of electrons that can dive into the depletion layer is nothing to do with is independent of the energy barrier height, and this energy barrier height is controlled by the supply the voltage, the reverse bias voltage. Okay, so if you measure how much current is flowing once reverse bias is applied across PN diode like that, -1 volt, -2 volt, -3 volt, whatever the reverse bias is, the magnitude of reverse bias doesn't matter in determining this leakage current or a very tiny amount of current flow. So that current is very well saturated, whatever the magnitude of reverse bias is, so that is named as a saturation current, I sub S. Or depending on the textbook, someone is writing down it as I sub naught. Okay, so in figure D, you can clearly see that the measure the current versus voltage characteristic of PN diode. So here in the forward bias, the current is exponentially increasing as forward bias is linearly increasing. But when the reverse bias is increased at a linear pace, whatever the magnitude of reverse bias is, always constant amount of current is flowing. In other words, saturation current is flowing. So this IV characteristic comes from the ideal PN junction diode. Again, ideal PN junction diode. In practical PN junction diode, the current voltage characteristic is quite not well matched to the IV characteristic of ideal PN diode. So we're gonna learn that some non-ideal factors and non-ideality in PN junction diode sooner or later in the upcoming lecture. Okay, so in this movie clip, you should understand, you should deeply understand how the current is forming across PN junction diode under forward bias and under reverse bias. And by drawing the energy band diagram, you should clearly show how the electrons and holes are moving toward the other side in the PN junction diode. And you should convince yourself with your own measured and estimated current voltage characteristic curve. How come the current is exponentially increasing under forward bias? How come the saturated current is flowing under reverse bias? Why is that? You should describe and write down your own sentences, the physical origin of this nonlinear behavior of PN junction diode. Okay, so please do that. And afterwards, please take the second movie clip. Okay, see you in the next movie clip. Bye bye.